right, so now let's talk about the residuals and a residual plot. Now, a residual is the difference between the actual value and the predicted value, also referred to as the error. And a residual plot is a plot of residuals versus the explanatory variable values or the predicted response values. So we'll take a look at what some examples look like here. But this is a p statistic, so just remember the residual equals actual minus predicted. And again, that little hat on the y there just means a predicted response. So this really translates down to, let's see, this is the error is the actual minus the predicted, AP stats. Okay, and the way we interpret residuals is just that the predicted response variable was this many units, or which was an under-over prediction of the actual by about this many units, etc. It's not very common to interpret the residual as much as it is to find the residual or to find the actual value from the residual. But nonetheless, since this is a prediction, there are some cases we can have here because I'm looking here at the relationship between y and y hat. So if this is an over prediction, my actual value is going to be less than the predicted value. But solving this backwards tells us that y minus y hat is less than or equal to 0. And I know that e equals y minus y hat. So if I'm over predicting, I'm actually going to have a negative residual, which feels counterintuitive. And if I'm under predicting, that means that my actual is greater than my predicted value. Again, I solve this, I move the y hat over, and I get that if I'm under predicting, I'm actually going to have a positive residual. So if you have a negative residual, that's over predicting. If you have a positive residual, that's under predicting. Here's the math behind it. It's a weird concept. So most times either just compute the residual itself, or if you're looking at your scatter plot and you can see the LSRL, just look at where your actual data point falls in relation to that LSRL there, that y hat, because that'll tell you whether you over predicted, which means that you would have a, if you over predicted, you're going to have a negative residual, and if you over predicted negative residual, under predicted positive residual. See what I'm saying? I teach this and I'm still always kind of wonky about it. So let's just look at our graphs and compute some things. Now, residual plots here. In order to determine the appropriateness of a linear model, we need to check two conditions. The first being that there's a fairly linear pattern in the scatter plot. And the second thing we want is that there's no evident pattern in the residual plot. And we want our errors to be completely random and scattered, just because if our errors are being predicted, that might be an indication that our data can be modeled by a different function, because it's y minus y hat. So for example, if you see a quadratic pattern, we can only get a quadratic pattern if it's x squared minus x, or x squared minus some value. But you can see there, because of the differences, the actual data might be modeled differently than the predicted data. So that's indicative of maybe some other transform being applied to your data set. So while both of these conditions are nice, at a minimum, only one of the above must be met. Now, if both are met, we have pretty much sufficient evidence that a linear model is appropriate. And so here are some examples of residual plots. And so these here, this red line is going to represent 0. And so this is a line of your residuals versus either x or y hat. You'll have at least one of your variables and then the errors amongst those variables there. So the first residual plot is a great example. There's completely random error, so there's no indicative pattern, meaning that a linear model is going to be an appropriate distinction for that data set. But when we look at these other 5 plots, these are not the only non-examples, but they're some of the more common ones. We can see that there's evident patterns in the linear plots, in the residual plots here. So we can see that even though, yes, this is linear, it's an evident linear pattern in the residual plot. So that's no bueno. This might mean that some other transformation's happening. Here we've got a nonlinear, appears relatively quadratic. So again, this would probably tell me that this is like x squared minus x, or x squared minus a constant. Here we have this funnel shape, meaning we lose predictive power, but then we're also able to tell, like, hey, as the further out we get, the less predictive we're getting. So our model's really only good at the initial starting point. Here we have this fan shape, also more of a funnel, kind of a combination of our funnel and this linear pattern here. And then we just have this weird wonky pattern. So if you see a pattern in your residual, Mayday, SOS, abort the mission, no bueno, go back and reevaluate your data. In this course, though, we're just determining the appropriateness of a model. We don't really have the tools yet to transform our data to the full effect. So in a scatter, you want a pattern. You want that linear pattern. And you want your residuals to rebel. You want them to be completely random. So random residuals, scatter equals pattern. Something like that. My students came up with it a few years ago. It was probably a lot catchier when they said it. But let's take a look at an example here. And this one's actually going to come to us from the 1999 FRQ from the stats exam. So Lydia and Bob used the years from 1990 to 1998 to predict the number of commercial aircrafts flying in the United States during those years. Year 0 corresponds to the year 1990, and the scatter plot reveals a constant proportional change among the observations. FYI, kind of linear there. Also, the following model is produced. Y hat equals 2939.93 plus 233.52x. So x is our year since 1990, and y hat is going to be the predicted number of aircrafts there. So here you can see we have only our residual plot, so I don't know much about the scatter plot, except that it reveals a constant proportional change, so got to be relatively linear there. Now, is a linear regression model appropriate? Why? And yes, a linear model is appropriate since, well, I don't know the scatter plot, but since there is no evident pattern in the residual plot. I'm going to run out of room here. Cool beans. So a linear model is appropriate because the residual plot reveals no evident pattern. Now let's find the predicted number of aircrafts in 1992. So that would be 2 years from 1990. So there x is going to equal 2. So let's go ahead and I'll change up colors here. So y hat is going to equal 2939.93 plus 233.52 times 2. So I'm going to predict for there to be about, let's see, I did my work previously. I'm going to predict for there to be about 3,406.97 aircrafts in the year 1992, which that seems relatively reasonable to me. Doesn't seem too large. I imagine there's at least that many aircrafts, if not more. And in theory, right, I can't have 0.97 aircraft, so I know for a fact there's probably 3,406 that can be accounted for. But that's my y hat there. Now, I've got my residual plot, and remember that our formula for the residuals is given by the following. And this is a very popular concept tested on the AP exam, either in the FRQ or in the multiple choice, but it's finding the actual amount. So here I know E equals Y minus Y hat. Well, for my residual plot, when X is 2, my residual is about 40. And also, we just used the prediction, our model to predict the number of aircrafts in 1992, which is about this many. So I can solve this equation here, and that tells me that the actual number of aircrafts in that year is probably going to be that residual plus the predicted value. So I'm going to take Y here, and I'll take my residual of about positive 40, and I'll add it to the predicted number here. And that's going to tell me that the actual number of aircrafts in 1992, assuming this model is correct, is going to be about 3,446.97 aircrafts. So that's the actual number there. So you can see they'll ask you predictions, they'll ask you to determine the appropriateness of your model, etc., and then find either the actual value or find the residual or interpret the residual. So what I have down here is an example for you determining residuals with their shoe size. This is the scatter plot, and you'll be able to tell if it's an over or under prediction. So go ahead, pause the video here, take some time to fill out this table, and then we'll bring it back to review together. Okay, so I started filling in these table values, and then I got bored, so I stopped. And as long as you can compute these values and understand where they're coming from, you'll be in good shape. So here what you can see is our scatter plot, and notice that here at 8.5, the actual value falls beneath the LSRL, so y hat would be greater than y, and this is a negative residual. Then here at 9, you can see that the one above is going to have a positive value, and the one below is going to have a negative. Same thing here, y is greater than y hat, so we should have positive. Here we're slightly under, negative. So if you're above the line, y minus y hat will be positive, as you can see here. But if you're below the line, you're going to have a negative residual. And next up, we were asked to find the residual for a man with a shoe size of 8.5. So from my chart here, 8.5 had an actual height of 66, predicted height of 67.255. I see that I get a residual of negative 1.255. That negative tells me that it was an over prediction. As we can see here, the prediction is greater than the actual. So the LSRL over predicted the height of a man with an 8.5 shoe size by about 1.255 inches. So even if you don't memorize or even understand the interpretation off the top of your head, you can see here that all we're doing is just describing what that value tells us. That value tells us that our model over predicted by this many inches, this many units, etc. So up until this point, now we can describe scatter plots, we can interpret our correlation coefficient, make predictions, including interpreting the slope and the y-intercept. We can make predictions, we can find the residual, and we can assess the appropriateness of a linear model. In the next lesson, we'll talk about 2 more summary statistics we obtain from our least squares regression units.